Problem 8a asks us to find the minimum angle where tonal internal reflection will happen between n2 and n3. You know that n1 sine theta is equal to n2 sine beta, theta being the angle between the normal where n1 and its value enters, and beta being the angle at which it leaves. Then you know that n2 sine beta is going to be equal to n3 sine of 90 because you want tonal internal reflection, meaning that none of the light will pass through the boundary of n3. So it'll all reflect back. Now you notice that n2 sine beta is in both of these equations, so instead of keeping the equations and solving for one and then the other, you can combine them to be n1 sine theta is equal to n3 sine of 90. Solve for theta. You find theta is equal to the inverse sine of n3 sine 90 over n1. And when you plug in the values for n1 and n3, you find that theta is equal to 50 degrees. For part B, we're asked to find when theta is the value you calculated in part A, we want to find the angle at which the A re-enters n1. So we will find that n1 sine theta is equal to n2 sine of beta. Since we already solved for theta, we can solve for beta. Beta is equal to this inverse sine of n1 sine theta over n2, which is equal to 30 degrees. Then you can solve for n2 sine beta is equal to n1 sine of 90 minus gamma. That's going to find the angle at which it will leave above the horizontal. Then when you move it over to solve for gamma, you find 90 minus gamma is equal to the sine inverse of n2 sine beta over n1. And then when you move the 90 over to the other side and divide by negative 1, you get gamma is equal to 90 minus the sine inverse of n2 sine beta over n1. When you plug in the values for n2, beta, and n1, you find that you get gamma is equal to 90 minus sine inverse of 2 times sine 30 over 1.3. And when that is solved, you get an angle of 40 degrees. So the light will exit n2 back into n1 at an angle of 40 degrees above the horizontal.